Hey everyone. So, in this lecture, what we're going to do is do a deep dive into the gradient descent algorithm, with the primary focus given this series being to, to try and get you up and running in terms of understanding gradient descent for machine learning and deep learning applications, right? So, gradient descent is an algorithm that is used, right, to train machine learning and deep learning models, right? And so, we'll start by first understanding the basic idea of what the gradient descent algorithm is, because gradient descent is not just used for machine learning and deep learning, it's used in a number of other applications. It falls under a category of problem called optimization problems, which by itself is a big discipline. And so we'll just start by understanding gradient descent in a general setting, and then we'll go and kind of take a problem which is focused on a machine learning basically example, and then we'll kind of code that up in Python and we'll implement it. We'll see how it works, right, and understand kind of variants of gradient descent as well. So let's get started. And so to get started, let's just start with a simple analogy or an example, right? So suppose you're a climber, you're on top of a hill, right? You're on top of this hill here. You've done a great job getting here. Now you're trying to go down, right? You want to get back home, right? You've done your hill climb. Problem is there's fog all around you, and so you can't really see all the way back down, right? So you're trying to find the quickest way down. Assume that you can, once you know the way, you're skilled enough to get down, right? So what do? Well, you look around you, right, and you say, well, in which direction is the gradient of the terrain, right, the steepest? In which direction does the hill decrease the quickest, right, the altitude? And what do? You say, okay, in this case, I believe this is the direction, and you're just going to go till you can see. You're just going to take just keep going till you get to that point. You're going to identify the point you're going to get to in the direction of the steepest gradient, and you're just going to walk down and get there. So you're going to climb your way down to that point. Now once you get there, you can see a little further, right? Now your visibility again is a little more because you've got to that point. So you say, okay, I'm going to stop going any further because at this point actually the terrain's starting to go up in a certain direction. Which direction is the terrain fall is falling the most? And you're going to say, okay, actually now I'm going to take a change and I'm going to move in this direction, leftward a bit in this case. And that's the best way down from this point. You take a few steps or one large step, and then you get to this point and you say, okay, now see here, I've hit this rock, it's going up in that direction. I'm going to change my direction and get back into this point, right? So you're going to take another step. You're going to keep doing that, and you've hit a spell where now it's actually relatively easy. It's a larger kind of step you can take. The gradient is nice and clear, the direction that is, and you're going to do one more step, and you're going to end up here in this, what looks like a small river, and you're going to follow that road. So, using this approach of finding the direction where you are, finding the direction of the steepest descent, or you're going to kind of move there, and then from that point on, take the next direction of the steepest descent and keep going till you head or till you kind of hit the bottom. So this is kind of the analogy, the physical analogy to steepest descent. Let's look at a mathematical problem, right? So think of this as that cliff, only it's quite simple. It's one dimensional. So your only variable is W, right? So all you can do is increase W or decrease W. And depending on that, your function in this case is going to change. The function is a simple quadratic function in one variable. So I'm using W here for the variable to stay consistent with machine learning or deep learning notation where W denotes the weights and so on. So the function is 3W squared plus 2W minus 5, which means for a given W, so if W is 2, you substitute W is 2 here and here, and you get a value. You can keep doing that and you can plot this function, and this function can keep going, but basically you see that at this point, we see the minimum of the function. So we've seen where the minimum is, but now assume that you don't know where the minimum is. You're at a particular point, you have a starting point of W. Can you get to this W mathematically, right? In a sensible way. And so an iterative, interesting way to do it is, suppose you're at a particular point. Well, we know that the gradient of the function, right, gives us the direction of the steepest increase or the fastest increase of the function, right? And that's for a typical function, Now this is a simple one-dimensional function. So the gradient is basically the derivative, right? It's df by dw. There's only one variable, so it's the whole derivative, which of this function is 6w plus 2. And if you don't remember your differentiation, you want to recap, I'll link the lecture we have done on basics of derivatives, so that will kind of get you up and running with derivatives. But it's a very simple term. You can use some rule to split this into these terms, and then you can get the derivative. These are simple polynomial derivatives. Right? So there's standard rules, and you can Google it or look at the notes or just use that lecture. So we've got the derivative. Now, this derivative basically at any point gives us the direction of the steepest increase. Right? What we want to do is get to the minimum, which means we want to decrease the function or get to the minimum. Right? From that point, we want to go in a direction of decrease. So if this gives you the direction of the steepest increase, you want to go in the opposite direction. So let's look at a couple of examples. What do we mean by this? Right? So this function, df by dw is 6w by 2. So that's the derivative. Let's take this point, w is 2, right? So what is df by dw? You substitute 2 in this expression. You get 6 times 2 is 12, plus 2 is 14. So you've got df by dw, that is the derivative, which is the gradient of the function is 14. What it tells us, what does it tell us? When it gives us your value, it also tells you the direction, which is the sign, right? So it tells you that by increasing w, when w becomes more positive, from this point, the function is going to increase. What do you want to do? You want to decrease the function. So you go in the opposite direction, right? Because we know the minimum is here, right? So clearly, if df by dw is positive, you go in the positive direction, you increase w, you're going further and further away from the minimum. So we've kind of intuitively, we can see that what we want to do is go in the opposite direction. We want to decrease w. What about if you're in this end, right? So now you're in the negative side of the function. The slope is different, right? So take w is minus 2. What do you get? So substitute minus 2 here. You get 6 times minus 2 is minus 12, plus 2 is minus 10. So now here the gradient is negative. What does it mean? It tells us, well, w is negative. If you go more negative, it's telling us the function is increasing, right? That's what the gradient indicates. It indicates the direction of steepest increase. So the direction is further negative. What do we want to do? We want to go towards the minimum. We don't want to increase the function. So again, you have to go opposite to that. You have to go in the positive direction. So it tells us, we've just seen here that in this direction, the derivative is positive. So it's telling us to increase the function, go to the right, increase w. So to decrease the function, you have to go to the left. What it tells us here is it tells us exactly the right thing. It tells us that in this case, the derivative is negative, which means we have to go further to the left, make w more negative to increase the function. We want to go to the minimum. We want to decrease it. So you go in the opposite direction. So basically, the direction of change that we want to go in to get to the minimum is you take this, the derivative gives you the direction of the quickest change, so steepest. But instead of ascent, which is increase, we are going in the opposite. We are going to descend in that direction, right? So let's take this point again and just try out how we do that, right? So w is 2. We have already computed df by dw. Just substitute w is equal to 2 here. You get 14. So we've learned that you want to go in the opposite direction. Can we do something as simple as this? Can we say w is, meaning the next w is this w we have 2 minus df by dw. What do you get? You get w is minus 12, which is not even on the plot, right? That's further, very, very far away to the left. And we know that here, as you increase w, actually the function is increasing. And this is a simple function, right? So you could have more complex functions where you can say it would come down. But in this particular example, w is only going to increase as you go further and further to the left. So what have we done? We have actually ended up increasing the function despite the fact that we have gone in the right direction. So what it tells us is choosing the right size of this step, meaning how much are we going to jump, is also very important. You can't just directly subtract that value because the scale could be completely off. So what do? We add a factor called the learning rate in machine learning. And in some cases, you also call it an optimization. Sometimes you just call it the step size. And this factor multiplies the derivative, right? So I'm using I for the current iteration, right? Because this is an iterative process. You're going to take a step, that's one iteration. And you're going to take another step, which is the next iteration, and so on. So at an iteration I, you have the W. So at the first, let's say if you start here, the WI is 2. You choose a step size, and there are ways to do it. You can just define a standard step size and say, I'm going to use this. Typically, there are more interesting algorithms that make the step size dynamic, right? And we'll kind of look at a few of them later in this lecture. So step size, alpha, and then the derivative of that function at that point. And what you get is the w at the next point. So that's the step you're taking to get your w at the next point. So let's kind of do this for this function step by step. So you're starting at x is 2. You're saying, I'm going to compute the function. So let's do that. You substitute x is equal to 2 in this function, and you end up at, the value here, right? So the function has a value of 11, right? What's df by dw? We've already calculated it's 14. Now what I'm going to do is, for this case, I'm just defining that the alpha, the step size, is 0.1. I know 0.1 works, right? So I'm going to choose 0.1. So what do you get? You get this term is actually the step you're going to take, right? So it's alpha times df by dw at this particular iteration. So there should be an I here, actually. It's an alpha I and df by dw. So it's 2 minus 1.4, which is 0.6. So you're here now already. That's quite a big step, right? Okay, great. What do you do now? Substitute that in this expression again. You're at I plus 1 now. Next iteration. The function now is minus 2.72. So you've already gone from 11 to minus 2.7. That's quite a jump. What's the derivative? The derivative is also smaller. It's 5.6. And so now the step you have is 0.1, which is the learning rate, times 0.56, times 5.6, which is 0.56. So now you subtract that from 0.6. This is this term, right? And so W minus this is 0.04, right? Great. Substitute that again in this expression. You see F becomes even smaller. And the dF by dW now is 2.24, which means the step you're going to take using the learning rate and the derivative is 0.224. So, if you do that, 0.04 minus 0.224 is minus 0.184. So you've now ended up here. As you can see, you're closer and closer to this minimum. So what are we seeing? We're seeing that as we take steps, we're coming closer to the minimum. We're also seeing something quite interesting. We're seeing that this learning rate, right, is there and it's constant. Yet the size of our steps is going down, right? The smaller and smaller steps. And that's because this derivative term gives us not just the direction, it also tells us how much we need to jump by in terms of step size. So this derivative, as we get closer and closer to the minimum, is becoming smaller and smaller because the function is starting to flatten out, right? It's getting closer to the minimum. And as this derivative is becoming smaller, your step size is becoming smaller. Because if you take a big step from here, you end up here, right? If you take a huge step like we saw in the first case where we didn't use a learning rate, you'd end up maybe further away, actually. Right? You could end up at a point where the algorithm does what is called diverging, right? In this case, it's called converging because it's coming closer and closer to a solution. It could diverge, meaning it could go further and further away, which is possible because, as we saw in that first example, right, where if you end up as minus 12, it's only going to get worse because the gradient then becomes larger and you're kind of taken further and further away from the solution. So let's take the next step, minus 0.184. Subtract this term, you get minus 0.2736. The function value you've got, and you see now that the function value, the change in the function value is much smaller as well, which you see in the plot, right? You're kind of coming closer and closer. The value of the function is now much closer, right? W is also much closer. So initially the function value was 11, right? Very far away. You're coming closer and closer. The function value is now minus 5.26, minus 5.32, right? df by dw has become smaller, and so the step size now is really, really small, right? 0.0358. Let's take that step. You end up at minus 0.3094. The function value is even is again changing a little more, but you're seeing that this is starting to converge to a 5.33, right? It's starting to that you're starting to see that the function minimum is around this value, right? Because the change in the function value is becoming much smaller. Again, the derivative is becoming much smaller. So you take another step. Now it's minus 0.3237. Again, as we said, minus 5.33, right? Take another step, and now that step is now really, really small. It's 0.00573. And you end up at minus 0.3294. So again, this is coming closer to minus 0.33, minus 0.323, minus 329, right? And so run it for a few more iterations, and you end up at the solution, which is minus 0.333, which is the value of W. And at that point, the function value is minus 5.333. You end up at the minimum. So we see how interestingly this function, you start off very far away, and initially you take these big steps because the derivative is large. And then as you get closer and closer, even with a constant learning rate, the derivatives are becoming smaller and you're converging, right, towards that solution. So let's visualize that. Well, you see the function, which we actually just did see in that plot. We saw how W and F are converging, but just to show you that with each iteration, in this case, you see that the function initially is changing quite a bit. And as it gets here, it's not changing, it's changing in the decimal, right? Which is why you don't really see it here. By the 10th iteration, it is pretty close to converging, right? Same with W. By the 5th, 6th iteration, it's changing very little. By the 10th, it's really started converging. You run it for a little more time and it'll really converge. Now, if you increase, in this particular example, if you decrease the learning rate, meaning you make it 0.01, it'll take a few more iterations and then it'll converge, right? Because the steps initially will also be smaller, right? And it'll converge, right? So do we choose a bigger learning rate or a smaller learning rate? Right? That's a question for you to think about. And then when we start implementing this, we'll come back to that question, right? And try and answer. And then what do we see? We see the derivative, right? So the derivative, we see that when it gets to the minimum, the derivative goes to zero, right? So at the convergence point, the derivative is zero. So that's an indicator that you've hit the minimum. And when we can look at this in the context of optimization, we'll see that the optimality conditions indicate that at a minimum for a function, right, the derivative is going to be zero for a convex, problem, right? And what is a convex problem? We'll get to that. But you see the function we had where it has a clear minimum, that's an example of a convex problem. Okay, so we have effectively, right, quite simply done a gradient descent algorithm for this function. We have found the minimum of this algorithm. This was not a machine learning or a deep learning problem. It's just finding the minimum of the function. And we've used the gradient descent algorithm for this simple one-dimensional problem, right, to get to the derivative by just doing this. We've started at an initial guess of W, and then we've fixed a learning rate, computed the derivative, taken a step in that direction, in the direction of the descent, and kept doing that, kept taking steps in the direction of the descent till we hit the minimum. So hopefully that's given you a good understanding of how, or at least given you a starting intuition into how a gradient descent method typically works. Now, what we have done is taken a simple function, right? In this case, it was a quadratic function in one variable. So it's a one-dimensional function, and found the minimum using gradient descent, right? Now, what we'll do is we're going to understand how that gradient descent. So we haven't covered a lot of the theory, right, in terms of how it works, in terms of optimization problems. Now we're putting a lecture on that. We're doing a small series on uh, optimization techniques in machine learning, right? Purely because there's a lot more detail related to optimization as well, or at least, and which I think it helps if you understand that. But adding that to this deep learning series is just going to complicate things for you. So for deep learning and machine learning, you should be fine just following how we now apply this to machine learning, and that's what we're going to do next. We're going to take a simple machine learning problem, fitting data to a this data basically for to fitting to this to a function, and we're going to train that model, right? And we're going to see now how we use gradient descent to do that. And then I'll share the links in this video as well to the short course on optimization for training machine learning and deep learning. So in that, if you're interested, you can get a little more understanding of the theory, right, of how an optimization problem works and how gradient-based optimization works and how this fits in. Okay, so part two will be out soon, right? I'm putting it as a separate lecture again because I think adding everything together makes it complicated, and part two is going to have quite a bit of coding. So it's going to be a fairly or decently long lecture. So stay tuned for that. Thank you.